All right, let's look at space curves. This is from chapter 13. And now we have done chapter 14. So chapter 13's materials look rather simple. So let's first have a summary of what chapter 13 is about. First, we need to represent a space curve. So the first one is representation. Okay. And how do we do that? If you remember, for a line, we had many forms like parametric form, vector form, symmetrical form. But for a curve, we usually just use the vector form. And by the way, the vector form and the parametric form, they are essentially the same. There is not really a big difference. Now, compare with surfaces, space curves are actually easier to imagine. We can always imagine that in a three-dimensional space, we have a moving object, say like a fly or an airplane. I think a fly is better because its trajectory is more complex. For an airplane, it's just straight. If a curve is obtained as the intersection of two surfaces, remember if we want a line, we have an intersection of two planes, right? So usually, if you look at two surfaces, they intersect, then the intersection is going to be a curve. We can try to make one variable as a parameter or introduce another parameter to represent the curve in the parametric form. We will see if we have an example later on. It's always easy to work with the curve using its parametric form. For example, in 2D, the unit circle in the polar coordinates, we have x is cosine t and y is sine t. Now, we are going to do calculus with the curve. So what kind of topics or concepts we can do with a curve? First of all, in this simple example, we're going to talk about tangent line and normal plane at a given point. If we have time, we're going to do arc length as well. There are more interesting objects we're going to discuss next time, and they are curvature and principal unit normal vector and binormal vector, and the fanciest one is so-called osculating circle. Now, we were talking about a curve is the trajectory of a moving object, so we can also find so-called velocity vector and speed and also acceleration. We may not discuss acceleration this time, but next time. Okay, so let's look at example 1. Sketch a diagram of the space curve. Illustrate on the diagram how to find the tangent plane and the normal plane at the point when t is pi over 4. Assume t is time and rt is the position of a moving object. Find its velocity and the speed when t is pi over 2. So let's first sketch a 3D coordinate system, y and z and x, like that. Okay, and then we're going to try our best to graph this curve over here. We start from t is equal to 0. So when t is equal to 0, we have rt is 2 and 0 and 0, right? So it's over here. We can say this is over here. It's 2, 0, 0 over here. Now, when t increases, then we will see that we have 2 cosine t for x and 2 sine t for y, and also t increases over here. Now, if we remember, 2 cosine 2t and y is equal to 2 sine 2t. This is a circle. circle of radius 2. That's what we see from x and y, but z is increasing. So this is what we have. Okay, so when t is equal to pi over 2, we will have 0 over here, and we have 2 over here. This is pi over 2. So we will try our best. So this is something like this. Okay, and it can go down. So this one actually is so-called a spiral, you can say, but it's really called a helix. This is called a helix. Okay. Now, over here, t is equal to this place over here, t is equal to 0. And over here, t is equal to pi over 2. So pi over 4 is somewhere over here. This place over here is t is equal to pi over 4. Okay. So now we're going to try to find the tangent line over here. So tangent line over here would be something like this. Okay, let me use a different color. So tangent line like this. Okay. So we wanted to find the tangent line's equation, but that's a question later to do. So what is the normal plane? Normal plane is the plane using the tangent line as the normal vector and also passes this point. So we can try our best to draw a normal plane. It's like this. Okay. This plane over here, the normal line, the normal vector is the tangent vector. It's the tangent vector. Okay. So now, how do we do that? From calculus, we know that if we want to look at an approximately this segment over here, we use the change of t. So what we have over here, we see that the direction vector of the tangent line is exactly its derivative. That's x prime of t, y prime of t, and z prime of t. Okay. The reason, of course, is this, because xt plus delta t minus xt, that's the vector that we see. That's the vector on the curve, yt plus delta t minus y of t, and z of t plus delta t minus zt. This is approximately the tangent line's directional vector, direction vector. And if we let delta t go to 0, and of course they should go to 0, but we will divide by delta t, then we're going to have it. That's why we have the derivative. Okay. So to find the equation of the tangent line, we are going to take the derivative. We have x of t derivative is going to be 2. Oh, I don't think we have cosine 2t. There's no 2 over here. Okay, just 2 cosine t. Negative sine t. And y prime of t is 2 cosine t. And z prime of t is pretty easy, and that's 1. Okay. So now let's find the directional vector at pi over 4. This is t. At t pi over 4, then we have x prime pi over 4. That's 2 minus root 2 over 2, right? And y prime of t at pi over 4, that's the same thing, 2 times root 2 over 2. and z prime of t is simply going to be 1. So we have this vector over here, v, and that's going to be negative root 2, positive root 2, and 1. Now we also need to know the point. So when t is equal to pi over 4, we have x, y, z. At that point is going to be root 2 over 2 times 2, and 2 root 2 over 2, and we know that t is pi over 4. Okay, so that's also from the formula. And then we will have this point over here is root 2, and pi over 4. And that's the coordinate over here. So this point over here is root 2 over 2, root 2 over 2, and pi over 4. These are the three coordinates. All right, now we can write down the equation, right? So the tangent lines equation is going to be x is equal to root 2 minus 2t. Y is going to be root 2 plus root 2t. And z is going to be equal to pi over 4 and plus t. Okay, that's the parametric form for the tangent line. Now how about normal plane? Normal plane, the same vector is a normal vector and same point. So what we have is x minus root x, negative root 2, plus root 2, y minus root 2, and plus 1, z minus pi over 4 equal to 0. Okay, so these are the basic objects at the point on the curve. Let's see if we have finished everything. Oh, we still have the last part. Assume t is time, r of t is the position of a moving object. Find its velocity and the speed when t is equal to pi over 2. That shouldn't be too bad. Let's try to squeeze it inside over here. Velocity vector is exactly the derivative. So we have over here 2 negative sine t and 2 cosine t and 1. So at pi over 2, t is equal to pi over 2, we have the velocity vector, and that's going to be negative 2 root 2 over 2 and 2 root 2 over 2 and 1. Simplify this, we have negative 2. Oh no, we got it wrong. Let me erase this. We are evaluating at pi over 2, not at pi over 4 anymore. So pi over 2, sine pi over 2 is negative 1. Yeah, so we have negative 2 over here. Cosine pi over 2 is 0, so we have 0 and 1. And what is speed? Speed is the magnitude of the velocity vector. So what we have is square root negative 2 squared plus 1 squared, and that's going to be root 5. And this is going to be the speed. All right, and that's for the first problem.